Tonight, we're going to talk about something that most people have never truly reckoned with, which is where the solar system actually ends. Most people have a picture in their heads. 8 planets, maybe the asteroid belt sitting between Mars and Jupiter, maybe Pluto hovering out at the edge. The solar system in that picture is a tidy collection of worlds orbiting the sun. And somewhere past Neptune or past Pluto, it just stops. Space takes over. That picture is wrong. Not slightly wrong. Not wrong in the way that a simplified map is wrong. Wrong in a way that changes what the solar system actually is. There is a structure surrounding our entire solar system that most people have never seriously thought about. It's called the Oort cloud. And here's the thing most people don't realize. It's not a small addition to the edges of what we know. It doesn't extend a little past Pluto. It extends so far beyond Pluto that Pluto, by comparison, is practically sitting in the sun's front yard. The Oort cloud reaches out to distances so enormous that the planets, all 8 of them, occupy only the smallest fraction of the space that still belongs gravitationally to our star. That's not intuitive. It doesn't feel right. And that's exactly the problem. Our brains are not built for this. We understand distances in miles, in hours of driving, maybe in flight times across oceans. We extend that into space with things like the distance to the moon or the distance to Mars. But the Oort cloud doesn't operate on any of those scales. It operates on a scale where even light, the fastest thing in the universe, takes over a year to cross from one side to the other. It operates on a scale where Voyager 1, launched in 1977 and traveling continuously ever since, won't even reach the inner edge of it for another 300 years. This isn't a matter of the Oort cloud being really, really far away. It's a structural reality. The solar system is not the tight collection of planets you were shown in school. It is an enormous gravitational empire stretching almost to the nearest stars, and the planets are just a tiny warm cluster near the center of it. Before this session concludes, you'll have grasped what that genuinely entails. Not just the number, not just the AU count or the light travel time, but the genuine conceptual weight of it. You're going to understand why calling the Oort cloud part of our solar system almost feels like a strange claim, even though it is one technically and gravitationally without any question. And you're going to understand why most people's mental image of where we live in space is missing something colossal. Before we get into it, if you're drawn to this kind of exploration the way we are, please give it a thumbs up or consider subscribing. It's a small thing, but it helps this reach more people who are genuinely curious about what's out there. We appreciate it more than you might think. Now, the Oort cloud is one of the least visited ideas in popular science, considering how fundamental it is. Most people have heard the name. Fewer know what it is. Almost no one has truly reckoned with its scale. And that's what tonight is about. Not just what the Oort cloud is, but what it means for the size of our solar system and for our understanding of where exactly we live. This is going to require setting up some tools first, some measurements, some comparisons, because the numbers involved stop working on their own after a certain point. You need anchors. You need reference points that your brain can actually hold on to before the larger numbers can land. We're going to build those anchors, and then we're going to use them. Now let's begin. Let's start with what most people picture when they hear the words solar system. There's a pretty specific image that comes to mind. The sun at the center, 8 planets arranged in neat concentric rings, maybe a dotted band for the asteroid belt somewhere between Mars and Jupiter. Saturn has its rings. The planets are labeled. Everything looks orderly, compact, and contained. That image comes from textbooks, from classroom posters, from museum displays and science documentaries, And it is deeply, fundamentally wrong, not in terms of which planets exist, but in terms of what the solar system actually is. Here's the first problem with that mental image. The diagrams are lying to you about distance, not accidentally, intentionally. If you drew the solar system to true scale on a standard piece of paper with the sun the size of a period at one end, Neptune would be off the page entirely. The distances involved are so extreme that fitting the planets into any reasonably sized illustration requires compressing the space between them by factors of millions. What looks like a manageable gap between Earth and Jupiter on a classroom poster is, in reality, about 390 million miles at closest approach. The poster doesn't tell you that. It can't. There's no way to show that and still have a usable diagram. So we grow up with a cartoon, a convenient compression that preserves the order of the planets but destroys any honest sense of the distances between them. And most of us carry that cartoon into adulthood without ever questioning it. The second problem is where most people's mental map stops. Ask someone where the solar system ends, and you'll hear one of a few answers. Some will say Pluto. Some will say Neptune, which is technically the last of the 8 recognized planets. Some have heard of the asteroid belt and figure things thin out somewhere around there. Very few people's intuitive boundary reaches past Pluto at all. That intuition made more sense 50 years ago. Pluto was discovered in 1930, and for decades it sat at the edge of the known solar system like a boundary marker. The next major structure beyond Pluto, the Kuiper Belt, wasn't confirmed until 1992. That's recent. In astronomical terms, it's practically yesterday. The Kuiper Belt is a region of icy bodies extending from roughly the orbit of Neptune out to about 50 astronomical units from the Sun. It contains Pluto. It contains hundreds of other objects comparable to Pluto in size. It's a substantial structure, and most people have never heard of it. Even among people who do know the Kuiper Belt exists, the mental map usually stops somewhere around there. 50 astronomical units out, past Neptune, past Pluto, out into the belt of icy debris. That feels like the edge. That feels distant. That feels like the frontier. It's not even close. Think about what the textbook image actually communicates. 8 planets, an asteroid belt. Maybe Pluto, depending on when you went to school. The image suggests that the solar system is a tidy, bounded structure with a clear center and a discernible edge. It suggests that the planets are the main event, that the space between them is essentially empty, and that once you get past the last planet, you've left the neighborhood. None of that is accurate. The solar system does not end at Neptune. It does not end at Pluto. It does not end at the Kuiper Belt. The gravitational reach of the Sun extends vastly, almost incomprehensibly, farther than any of those landmarks. The territory our star controls, the region where objects remain in orbit around it, stretches to distances that make the planets look like they're all huddled together in a single small corner. What we call the solar system on those posters and diagrams is really just the innermost slice of a much larger structure. The planets, the asteroid belt, Pluto, the entire Kuiper Belt, all of it compresses into a zone that represents only a small fraction of the full extent of solar gravitational influence. Everything beyond the Kuiper Belt, the vast majority of the volume that technically belongs to our star, gets left off the diagram entirely. Not because it isn't real, because it's so enormous that there's no intuitive way to represent it alongside the planets and still have it mean anything. That's the problem we're working against. The image most people carry is accurate as far as it goes. The planets are in the right order. The Sun is in the middle. but the frame of the picture cuts off almost everything. It's like showing someone a map of a continent and cropping out 95% of the landmass because it wouldn't fit on the page, and then letting them believe what they're seeing is the whole thing. The Kuiper Belt's confirmation in the early 1990s started to push that frame outward, but even now, decades later, the public understanding of where the solar system ends hasn't caught up. Most people's mental model is still basically the same poster that was hanging in classrooms in 1975. The real solar system, the full extent of it, the gravitationally bound territory around our star, is something else entirely. Uranus extends that further. Uranus sits at around 19 astronomical units. Now we're talking about a planet that is 19 times the Earth-Sun distance from our star. Light from the Sun takes about 2 hours and 40 minutes to reach it. When you look at Uranus through a telescope, the light you're receiving is nearly 3 hours old. At that distance, you wouldn't feel the sun's warmth at all. The solar wind is weakening. The environment is starting to look genuinely alien. Here's the thing about the Oort cloud that most people, even people who've heard of it, don't fully appreciate. It isn't just far. It isn't just really, really far. The distance involved is so extreme that the words we normally use to describe space simply stop working. You've spent the last few minutes building a mental ruler. Mars at 1.5 astronomical units, Jupiter at 5, Saturn at 9.5, Pluto at 40, the outer Kuiper Belt at roughly 50. That ruler was useful. Now you need to understand that it's about to become almost useless. The inner edge of the Oort cloud sits somewhere between 2,000 and 5,000 astronomical units from the Sun. Let that settle for a moment. Pluto, which most people still think of as being at the edge of the solar system, sits at around 40 astronomical units. The inner edge of the Oort cloud starts at 2,000. That means the Oort cloud doesn't begin until you are 50 times farther from the Sun than Pluto. 50 times. Not 50% farther. 50 times the distance. Think about what that means on the ruler you just built. Every planet in the solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, fits within the first 30 astronomical units. Pluto is at 40. The Kuiper Belt extends out to maybe 50. And then there's a gap, an enormous, staggering gap. And on the other side of that gap, at 2,000 astronomical units, is where the Oort cloud begins. Here's a comparison that might help it land. The Kuiper Belt is roughly 1 astronomical unit wide in some estimates. 1 astronomical unit. The distance from the Earth to the Sun. That entire structure, everything we consider to be beyond Neptune, a region that took decades to confirm, fits within a span of space about 93 million miles thick. The Oort cloud, by contrast, extends from 2,000 astronomical units out to somewhere around 100,000 astronomical units. That's a width of roughly 98,000 astronomical units. The Oort cloud isn't just bigger than the Kuiper Belt. It is somewhere between 100 and 10,000 times wider, depending on how you measure. If you wanted a physical analogy, imagine the Kuiper Belt is the doorstep of a house. The doorstep is maybe 2 feet wide. Now imagine the Oort cloud. The Oort cloud's outer edge would be somewhere on the other side of the continent. Not down the street, not in the next city. Across the entire continent from one coast to the other. And the doorstep, all of the planets, all of the asteroid belt, all of Pluto, the entire Kuiper Belt, is sitting right there at the entrance, occupying almost no space at all relative to everything that follows. That's what we're dealing with, and most people have never once thought about it this way. Here's another way to frame it. You've probably heard that the solar system is enormous, and it is. The distance from the Sun to Neptune alone is about 2.8 billion miles. That sounds vast. But Pluto's entire orbit, that ellipse it traces around the Sun over 248 years, fits comfortably inside the opening boundary of the Oort cloud with room to spare. Pluto's orbit is contained within a region that doesn't even qualify as the beginning of this structure. It's like saying you've crossed the lobby when the building has another 1,000 floors above you. Some people hear 2,000 astronomical units and still don't feel the weight of it. So let's try numbers. 1 astronomical unit is 93 million miles. At 2,000 astronomical units, you are 186 billion miles from the Sun. That's 186 billion miles. At the outer edge of the Oort cloud, somewhere around 100,000 astronomical units, you are talking about roughly 9.3 trillion miles. That's 930 billion miles. For comparison, Alpha Centauri, our nearest stellar neighbor, the destination of every interstellar fantasy, sits about 25 trillion miles away. The outer Oort cloud extends more than a third of the way there. That's not a metaphor. That's the actual geometry. The solar system doesn't stop near the planets. It doesn't stop at Pluto. It extends so far into space that its outer regions are genuinely competing in terms of sheer distance with the gap between stars. And this changes what the solar system actually is. When astronomers talk about gravitationally bound territory, the space where our sun's gravity dominates, where objects are technically still in orbit around the sun, they're talking about a volume of space that includes the Oort cloud. All of it. That means the solar system, properly defined, is not a cozy collection of planets sitting in a relatively compact arrangement. It is a structure that, in its outer reaches, approaches interstellar distances. The planets are an almost insignificant feature of it, clustered near the center, relatively warm, relatively dense. But they are surrounded by this vast frozen shell that dwarfs them entirely. When you compare the volume of space occupied by the Oort cloud to the volume of space occupied by everything else we call the solar system, the planets and the Kuiper belt amount to a rounding error. The Oort cloud is not an appendage of the solar system. It's closer to the truth to say that the planets are an appendage of the Oort cloud. So when someone tells you the Oort cloud is at the edge of the solar system, understand what that actually means. The edge they're describing is something so remote that our fastest spacecraft, after nearly 50 years of continuous travel, hasn't come close to touching it. It begins at 2,000 astronomical units, where everything familiar is long behind you. And that number, 2,000 astronomical units for the inner edge, that's not the end of the Oort cloud. It's barely the beginning. The Oort cloud is not a single uniform structure. Most people, when they first hear the distances involved, picture something like a fog, a vague, diffuse scattering of debris spread randomly across the outer solar system. That's not what it is. The Oort cloud has architecture. It has layers. And understanding those layers changes how you think about every comet that has ever crossed the inner solar system. Here's where things get interesting. Astronomers divide the Oort cloud into two distinct regions. The inner region, which begins at roughly 2,000 astronomical units and extends to somewhere around 20,000 astronomical units, is called the Hills cloud. That name comes from astronomer Jack Hills, who did the theoretical work to establish this inner region as a separate structure with its own characteristics. The outer region runs from about 20,000 astronomical units all the way out to somewhere between 50,000 and 100,000 astronomical units. And these two regions are not just different in terms of distance. They're different in shape, in density, and in how they got to be what they are. Start with the Hills Cloud. It's shaped like a torus, a thick, flattened ring, like a donut wrapped around the solar system but with real depth to it. That shape isn't a coincidence. At distances of 2,000 to 20,000 astronomical units, the Sun's gravity is still strong enough to matter, and more importantly, the gravitational plane of the planets still has some influence. Objects at these distances haven't been completely pulled free of the structure that governs the inner solar system. They're far out, but not so far out that the geometry of the planetary disk has stopped shaping where they end up. The result is a flattened distribution, objects concentrated more toward the orbital plane than spread out in a perfect sphere. Now look at the outer cloud. The shape is completely different. It's a true sphere, not flattened, not disk-like, but a full three-dimensional shell surrounding the solar system in every direction equally. Objects above the poles of the solar system, objects below the equatorial plane, objects at every angle. If you could look at it from outside, the outer Oort cloud would look like a giant bubble with the sun and all 8 planets sitting somewhere near the center. And that spherical shape is the key to understanding what happened to this region over billions of years. Here's the thing most people don't realize about why the outer cloud is shaped that way. It wasn't born spherical. Objects originally flung outward from the inner solar system would have retained some memory of the orbital plane they came from. They would have been on elliptical inclined orbits, but still showing some preference for the plane of the planets. What changed them was time and gravity, specifically the gravity of the galaxy itself. The Milky Way is not just a backdrop. It has mass, enormous, distributed mass. And that mass exerts gravitational forces on objects far from the Sun, forces that are negligible in the inner solar system, but become meaningful at distances of tens of thousands of astronomical units. Over billions of years, the galactic tide, that diffuse gravitational pull from the mass of the galaxy surrounding our solar system, tugged at the orbits of objects in the outer Oort cloud. It bent those orbits. It rotated them. It gradually stripped away the memory of the original orbital plane and left behind something much more random, much more isotropic, evenly distributed in all directions. The sphere is a fossil of galactic influence acting on solar system debris for 4.5 billion years. That's the shape of the cloud being carved by forces operating on a galactic scale. The timescales involved are as important as the forces themselves. 4.5 billion years is long enough for the galactic tide to reshape entire populations of objects. But that reshaping is ongoing. The process doesn't stop. Every orbit in the outer Oort cloud is slowly being adjusted, rotated, and randomized by the steady gravitational influence of the Milky Way's disk and bulge. What we observe today is not a finished product, but a system caught in the middle of a continuous transformation that began when the solar system formed and will continue for as long as the galaxy exists. Now consider the density. This is where the two regions differ in a way that matters enormously. The Hills cloud, despite covering less volume, is believed to contain the majority of the total population of Oort cloud objects. Estimates vary, but a rough working number suggests that something like 5/6 of all the icy bodies in the Oort cloud are packed into that inner region. The outer cloud, despite being vastly larger in volume, is more sparse. 1/6 of the estimated population spread across a space so much bigger that the objects are genuinely far apart from each other. The outer cloud isn't empty, but on average, the distance between any two objects out there is enormous. You wouldn't see neighbors, you'd see one object, and then you'd travel an enormous distance before finding another. Think about what that means for the shape of this system. You have a dense, flattened inner torus, the Hills cloud, packed with the bulk of the Oort cloud's population, sitting between 2,000 and 20,000 astronomical units from the Sun. And then surrounding that in all directions, a vast, thin, spherical shell extending tens of thousands of astronomical units further, holding the remainder in a diffuse, galaxy-sculpted envelope. It's a layered system, structured, not random, and the objects in each region don't behave the same way. Objects in the Hills cloud are more tightly bound to the Sun. They're harder to dislodge. Getting something from the inner Hills cloud down into the inner solar system requires a significant perturbation, a major gravitational nudge. Objects in the outer cloud are barely hanging on. They're so far from the Sun that the Sun's gravity on them is extraordinarily weak. A relatively modest gravitational nudge from a passing star or from the slow pull of the galactic tide is enough to change their orbit significantly, enough sometimes to send one of them falling inward. That distinction between the inner and outer regions matters enormously when you start trying to understand how comets find their way into the inner solar system. There's a better way to think about these distances than stacking up numbers like 50,000 astronomical units or 100,000 astronomical units. Because after a certain point, the numbers simply stop working on the human brain. What actually works is light. Nothing in the cosmos travels faster than light, which speeds along at roughly 186,000 miles per second. No known object can match its pace. And when you use light as your measuring stick, the true scale of the Oort cloud becomes something you can actually feel. Start close. Light leaving the Sun right now takes about 8 minutes to reach Earth. That's the baseline. 8 minutes to cross 93 million miles. It's already a staggering distance by any human standard, but by the standards of what we're building toward, it's nothing. Now push out a little further. Light takes roughly 4.5 hours to reach Neptune's orbit. Neptune, the outermost planet, the one that sits at 30 astronomical units, 4.5 hours at the speed of light. Hold that in your mind. The entire span of the known planetary solar system, everything from Mercury out to Neptune, fits inside a 4.5-hour light travel window. All 8 planets, every world humans have ever studied up close. That's the size of what most people call the solar system. Now here's where things start to shift. Light from the Sun takes roughly 10 to 28 days to reach the inner edge of the Oort cloud. Not hours, days. The same light that crosses the distance between the Sun and Earth in 8 minutes takes weeks to get to the beginning of the Oort cloud, the inner edge, the near side. That alone should recalibrate something in your thinking. We're not talking about a modest extension of the planetary neighborhood. We're talking about a structure that begins where the light travel time jumps from hours to weeks, and the outer edge is further still. Light from the Sun takes potentially a 1.5 years to reach the Oort cloud's outer boundary. Think about that for a second. One full Earth orbit around the Sun, then half of another. That's how long the Sun's own light takes to cross the full depth of this structure. The Earth has moved through an entire cycle of seasons, and then some, by the time a photon leaving the Sun today makes it to the far edge of our solar system. That's what we're dealing with. Consider another way to visualize this. If we reduce the Sun to a marble, Earth would be a grain of sand about 30 feet away. Neptune would be another grain sitting roughly 900 feet distant. But the Oort cloud's inner boundary would place that grain of sand more than 2 miles from the marble. The outer boundary would stretch nearly 10 miles beyond. When you rescale everything proportionally, the solar system's true geometry emerges. We inhabit a realm where empty space overwhelmingly dominates all the solid matter contained within it. Here's the thing. Most people don't fully process when they hear that. Light doesn't slow down. It doesn't get tired. It doesn't stop to refuel. At 186,000 miles per second, it is moving faster than anything we can engineer or imagine engineering. And it still needs the better part of 2 years to pass through the Oort cloud from one side to the other. That means the Oort cloud is not just large by the standards of planets and asteroid belts. It is large by the standards of light itself. There's an analogy that makes this easier to grasp. Imagine the solar system is a country. The sun is the capital city. Earth is a neighborhood close to downtown. The other planets stretch out across the metro area. Neptune is on the far outskirts, maybe an hour outside the city center. The Kuiper Belt is where the suburbs finally give way to open land. And the Oort cloud. The Oort cloud is everything from that city limit to the national border thousands of miles away. The planets, all of them, exist in the same metropolitan area. The Oort cloud is the rest of the country. And not just a little bit of the country, most of it. By volume, by extent, by the sheer fraction of the solar system's territory, the Oort cloud is dominant. The planets and everything else we typically call the solar system occupy a tiny fraction of the gravitationally bound space around our star. The Oort cloud accounts for the overwhelming majority of that space. It surrounds everything else. It encompasses every planet, every moon, every spacecraft we've ever launched, and it dwarfs all of it combined. What the light travel framework does is force you to reckon with that in a way that astronomical units counts don't. When someone says 100,000 astronomical units, your brain doesn't have a reference. When someone says light takes a year and a half to cross it, you do have a reference. You know what a year feels like. You know that light is fast. Putting those two things together creates something the numbers alone never achieve, an actual visceral sense of the scale involved. So let's be precise about what this means. The planetary solar system, the thing most people picture when they close their eyes and imagine where we live in space, has a light travel diameter measured in hours. The Oort cloud has a light travel diameter measured in years. That is not a modest difference. It's not a factor of 2 or 3. The Oort cloud is hundreds of times wider than the entire planetary solar system, measured in units of time it takes light to cross. It is an entirely different order of magnitude from the structure we typically call home. When you put it that way, the Oort cloud isn't a distant curiosity at the edge of our solar system. It's a structure that operates on a completely different scale from everything else we call home. Here's something remarkable about the Oort cloud that doesn't get discussed nearly enough. We've spent time talking about the scale of this structure, the distances, the light travel times, the numbers that strain human comprehension. But here's the thing. Most people don't stop to consider. Nobody has ever seen the Oort cloud. Not directly, not once. Not a single object has been definitively confirmed to actually reside there. Everything we know about it, the distance, the structure, the population, the shape, was inferred, deduced, worked out on paper from the behavior of things falling inward toward the sun. That's not a minor footnote. That's the entire story of how this enormous structure was discovered, and it's one of the most striking examples of scientific reasoning in the history of astronomy. To understand how that happened, you have to go back to 2 astronomers working decades apart, starting with Ernst Öpik. Öpik was an Estonian astronomer born in 1893, and by 1932 he had already begun thinking carefully about a problem that had nagged at astronomers for a long time. Where do comets come from? Not the short-period ones that return every few decades, but the long-period ones, comets with orbital periods stretching thousands or millions of years, arriving from seemingly random directions. Opic reasoned that a reservoir had to exist. Something had to be storing these objects at enormous distances from the Sun, releasing them occasionally into the inner solar system. He published this idea in 1932, proposing that a distant cloud of cometary bodies surrounded the solar system at very large distances. The reasoning was sound, but Opic didn't push it further. He didn't work out the mathematics in enough detail to establish where exactly this reservoir would need to be, how large it would have to be, or what could be causing comets to fall inward from it. The idea sat there, largely unnoticed, for nearly 2 decades. Then Jan Oort took it up. Oort was a Dutch astronomer working at Leiden Observatory, and in 1950 he did something that seems almost impossibly precise given what he was trying to figure out. He analyzed the orbits of 19 comets. That's it. 19. From those 19 orbits, he noticed something that nobody had clearly articulated before. 10 of those comets were fresh. They weren't returning visitors. They were coming in for what appeared to be the first time, and their orbits pointed back to the same region, an enormous distance from the Sun, somewhere in the range of tens of thousands of astronomical units. The same region, not scattered randomly, clustering around a specific, very distant zone. That clustering was the key. Think about what that means. If comets were just drifting in randomly from interstellar space, their aphelia, the farthest points of their orbits, would be distributed in all directions at all kinds of distances. There would be no clustering, but there was clustering, and clustering meant a source, a common reservoir that these objects were being dislodged from and sent inward. Oort calculated where that reservoir would have to be and what properties it would need to have to explain what he was observing. The result was the cloud that now bears his name, a vast spherical shell surrounding the solar system at distances of roughly 20,000 to 100,000 astronomical units. He published his findings in 1950, and this time the astronomical community paid attention. Here's where things get genuinely extraordinary. Oort's conclusion was not based on observing the cloud itself. He couldn't observe it. The objects there are too small, too dark, and too far away. Even today, with our most powerful telescopes, we cannot directly detect them. What Oort observed were the comets that had already left the cloud, the ones that had fallen inward, crossed the entire solar system, and were passing close enough to the Sun for astronomers to study their orbits. He worked backward. He looked at the trajectories of incoming objects and traced them back to where they must have originated. It's like standing at the bottom of a mountain watching rivers flow downhill and reasoning that there must be a lake or a glacier somewhere at the top. Not because you've seen it, but because the water has to be coming from somewhere, and the flow tells you where. This kind of reasoning has a long tradition in astronomy. Neptune was discovered because astronomers noticed anomalies in Uranus's orbit and calculated where a gravitational influence must be coming from. The existence of dark matter was inferred from the rotational behavior of galaxies long before anyone proposed a direct detection method. But the Oort cloud stands out even in that company because it was postulated not from a single anomaly in one object's behavior, but from a statistical pattern across a small set of comet orbits. 19 comets, 10 of them fresh. That was enough. It's also worth giving proper credit to the full name that some astronomers use for this structure, the Opic-Oort cloud. Opic got there first in 1932 with the conceptual framework. Oort built the mathematical case 18 years later. Both of them reasoned their way to the existence of something they would never be able to see. And that's still where we stand today. Decades after Oort's 1950 paper with telescopes orders of magnitude more powerful than anything he had access to, the Oort cloud remains unobserved in any direct sense. We have not photographed it. We have not sent anything to it. We know it exists because the math demands it, because comets keep arriving, because their orbits point back to a common region, because the numbers work out the same way Oort showed they would in 1950. A conclusion arrived at entirely through reasoning from data, with no direct observation at all. That makes it one of the most elegant deductions in the history of astronomy. To understand why the Oort cloud had to exist, you first have to understand the problem that astronomers were trying to solve. Comets don't last forever. That's the core of it. Every time a comet swings through the inner solar system and passes close to the sun, it loses material. The sun's heat vaporizes the surface ices, blasting gas and dust outward into that glowing tail we find so spectacular from Earth. That tail is beautiful. It's also the comet destroying itself. Each pass near the sun strips away more material, and eventually there's nothing left. Just an inert, dark rock tumbling through space, or nothing at all. Some comets break apart entirely under the thermal stress. Others get ejected from the solar system when a gravitational encounter with Jupiter gives them more velocity than the sun's gravity can hold. Some collide with planets. There are several ways a comet story ends, and none of them involve the comet surviving indefinitely. Here's the problem. They kept showing up anyway. Throughout all of recorded human history, thousands of years of sky watching, from Babylonian astronomers to Greek philosophers to medieval monks writing down anything unusual they saw overhead, comets kept appearing. New ones, bright ones. Comets that had never been recorded before and would never be recorded again. If comets were being steadily consumed and destroyed, the supply should eventually run dry. But it wasn't running dry. Something was replenishing it. Astronomers understood this for a long time before they had any real answer. The question sat there, unresolved, through centuries of increasingly sophisticated observation. Where were all the new comets coming from? To answer that, you need to understand that not all comets are the same kind of object. Astronomers divide them into two broad categories based on how long their orbits take. Short-period comets complete a full orbit around the Sun in under 200 years. Halley's Comet is the most famous example, returning every 75 to 76 years on a predictable schedule. These short-period comets tend to travel in orbits that are roughly aligned with the plane of the solar system, the same flat disk where the planets orbit. That alignment is a clue about where they came from. Objects in short-period orbits have generally been shaped and captured by the gravitational influence of the giant planets, particularly Jupiter, which tends to pull things into orbits that share its general geometry. Most short-period comets are thought to originate in the Kuiper Belt, the disk of icy bodies beyond Neptune, rather than from truly distant space. Long-period comets are a completely different story. These are comets with orbital periods exceeding 200 years, and in many cases far, far longer than that. Some have orbital periods measured in hundreds of thousands of years. A few appear to be on orbits so elongated that this might be their first pass through the inner solar system since the solar system formed. These are comets that have spent billions of years in cold storage somewhere very far away, and something finally nudged them inward. What makes long-period comets so revealing is their direction of arrival. Short-period comets come from the same general plane as the planets. Long-period comets arrive from every direction, above, below, sideways, at angles that have nothing to do with the orbital plane of the planets. They come from all across the sky, uniformly distributed across a sphere. That pattern is the smoking gun. If comets were coming from a disc-shaped region, you'd expect them to arrive from a narrow band of sky. But they don't. They come from everywhere. That means their source is not a disk. It's a sphere. Something out there surrounding the solar system in all directions is producing them. Think about that for a second. The only way to get objects arriving from all directions equally, above the solar system, below it from the sides, is if their source is a spherical shell enclosing the solar system entirely. There's no other geometric explanation that fits the data. A disc-shaped source would leave a signature. A point source would leave a signature. A sphere leaves exactly the pattern astronomers were seeing. Comets from everywhere with no preferred direction. That's the logical structure of the argument. If long-period comets arrive from all directions, they originate in a spherical reservoir. That reservoir has to be at an enormous distance because these comets have orbital periods stretching into the millions of years, and their aphelia, the farthest points of their orbits, reach to tens of thousands of astronomical units. And that reservoir has to be vast enough to keep supplying fresh comets, despite billions of years of losses. When Oort ran the numbers on 19 comet orbits in 1950 and found that 10 of them seemed to be coming from roughly the same enormous distance, he wasn't discovering something entirely new. He was solving a problem that had been accumulating evidence for a very long time. The Oort cloud isn't a random discovery. It's a required answer to a logical paradox. Comets are destroyed. Comets keep appearing. Therefore, something is making new comets available. The something is a vast spherical shell of icy objects at the outer edge of the solar system, gravitationally bound to the sun but far enough away that the slightest disturbance can send them falling inward over millions of years. The mechanism for the replenishment, the geometry of the source, the scale required to sustain it. All of it follows from the comets themselves, from the direction they arrive, from how long their orbits take, from the fact that they show up fresh and bright, carrying volatiles that haven't been cooked by sunlight before. That's what the Oort cloud is, the answer to a question that had been accumulating for generations of skywatchers. Now let's talk about how all of those objects got out there in the first place, because this is where the story gets genuinely strange. The assumption most people make is that the Oort cloud is simply where the solar system's outer material settled, that the objects out there formed at those distances far from the sun, in the cold and the dark. That's a reasonable assumption. It's also completely wrong. The objects in the Oort cloud did not form there. Not a single one of them. They formed in the inner solar system, in the same region that produced the planets, and they were driven outward by forces that fundamentally reshaped the entire structure of our solar neighborhood. To understand this, you need to go back about 4.6 billion years. The sun was newly formed. Surrounding it was a vast rotating disk of gas and dust, the protoplanetary disk. This disk was the raw material for everything we now call the solar system. Gravity pulled clumps of that material together. Small clumps became bigger clumps. Bigger clumps swept up more material and grew into planetesimals, rocky and icy bodies kilometers across. Some of those planetesimals kept growing, pulling in more and more mass, and eventually became the planets. But the disk had far more material in it than what ended up in the 8 planets. There were countless smaller bodies left over, planetesimals that were too small, too slow, or simply in the wrong place to join the growing planets. And this is where things get violent. The gas giants were growing fast. Jupiter in particular accumulated mass at a rate that gave it gravitational dominance over a huge region of the solar system. As Jupiter grew, its gravity didn't just pull nearby material toward it. It flung material outward with enormous force. A planetesimal drifting near Jupiter didn't have many good options. It could collide with the planet. It could be thrown toward the sun. Or it could receive a gravitational kick so powerful it was sent flying outward onto an orbit that carried it far beyond the reach of the planets. Some of those objects reached escape velocity entirely and were lost to interstellar space. Gone. But many were not quite fast enough to escape. They went outward on highly elliptical orbits, stretched so far from the sun that they barely held on gravitationally, swinging out to distances measured in thousands of astronomical units before falling back inward. Over millions of years, object after object received this same treatment. Here's the thing most people don't realize about this process. It wasn't rare, it wasn't occasional. It was happening on an enormous scale throughout the period when the giant planets were forming and settling into their current orbits. The early solar system was chaotic in a way that's hard to fully appreciate. The planets weren't stationary. Jupiter migrated. Saturn migrated. Their orbits shifted, and every shift sent gravitational shockwaves through the surrounding material. Planetesimals that had been orbiting quietly suddenly found themselves on new trajectories. The population of small bodies in the inner solar system was being systematically sorted and scattered, with vast quantities of material being thrown outward into the distant reaches of the sun's gravity. And slowly, over millions of years, those objects accumulated in what we now call the Oort cloud. Not because it was a natural gathering point, not because conditions out there were favorable for forming these objects, but because objects thrown to those distances had nowhere else to go. They couldn't escape, and they couldn't come back without being scattered again. They were gravitationally stranded. What happened next is equally important. As these objects settled into their distant orbits, another set of forces began to act on them. The sun's gravitational grip, already weakened enormously at these distances, had to compete with the tidal forces of the Milky Way itself. Nearby stars, passing at various distances over billions of years, exerted their own gravitational tugs. These influences gradually changed the shapes of the orbits, pulling them away from the highly elliptical paths they'd arrived on and rounding them into something more stable. The outer cloud became spherical not because of anything the sun did, but because of what the galaxy did. The objects were being shaped by forces operating on scales that dwarf the solar system entirely. But that's the next part of the story. What matters here is what this origin tells us about the Oort cloud, because it reframes everything. The Oort cloud is not a formation zone. It's not where the solar system built its outer structure in some orderly fashion. It's a dumping ground, a gravitational exile. Every object out there was thrown out during a period of violent rearrangement in the early solar system. Material that couldn't become a planet, couldn't escape entirely, and ended up stranded in the deep freeze at the edge of the sun's gravitational reach. These are the leftovers of solar system formation, preserved at temperatures near absolute zero, roughly 4.5 billion years old, essentially unchanged since the day they were flung outward. Think about what that means. When a comet falls inward from the Oort cloud and sweeps through the inner solar system, trailing a tail of vaporized ice across the sky, you're looking at a piece of the original protoplanetary disk, material that was present when the sun first ignited, when Earth was still a molten ball of colliding rock. The Oort cloud is a fossil record. It preserves at enormous distance the raw conditions and composition of the early solar system in a way that nothing in the inner solar system can. Planets have been geologically active, melted, reformed, and transformed over billions of years. The Oort cloud objects have just been sitting there, frozen and undisturbed, in conditions that haven't changed meaningfully since the solar system was young. That's what the Oort cloud actually is. Not an outer boundary drawn at some arbitrary distance, not a region of space that happened to collect debris. It's a graveyard for the building material of our solar system, preserved at unimaginable distances because the early gas giants were powerful enough to throw it there, and the sun was just barely strong enough to hold it. The objects we now call the Oort cloud were not born in the Oort cloud. They were born much closer to the sun, and then they were thrown away. Jupiter is, more than anything else, why the Oort cloud exists. We talked about how the objects out there didn't form in the Oort cloud. They formed much closer in, part of the same swirling disk of gas and dust that built the planets. But something had to move them. Something had to take billions of small rocky and icy bodies and fling them to the outermost reaches of the solar system. And that something was Jupiter. Here's where you need to think about what Jupiter actually is. It's not just a big planet. Jupiter contains more mass than all the other planets in the solar system combined, more than twice the mass of everything else orbiting the sun put together. When Jupiter finished forming, roughly 4.6 billion years ago, it didn't just sit there quietly. Its gravity reached into the surrounding region like a massive hand, grabbing at anything that drifted too close. The early solar system was crowded. Planetesimals were everywhere, billions of small icy and rocky bodies, ranging from a few kilometers across to hundreds. These objects were moving on orbits that crossed and shifted constantly. The planets were still settling into their final positions. Everything was dynamic, chaotic, and unstable. And Jupiter, with its enormous gravitational influence, was the dominant force shaping what happened next. When a planetesimal drifted into Jupiter's gravitational neighborhood, the outcome depended entirely on the geometry of the encounter. The angle, the speed, the distance from Jupiter at closest approach, all of it determined where the object ended up. And the range of possible outcomes was enormous. Some objects got kicked directly into the sun. Jupiter's gravity bent their trajectories so sharply that they fell inward, consumed before they ever had a chance to become anything else. Others were thrown into the inner solar system and collided with the rocky planets, including early Earth. Some researchers believe a significant portion of the water in Earth's oceans arrived this way, through impacts from icy bodies that Jupiter had redirected inward. Others were ejected completely. They received enough of a gravitational boost to exceed escape velocity. They left the solar system entirely, drifting off into interstellar space where the sun's gravity no longer had any claim on them. But there was another category. A large fraction of these planetesimals received kicks that were powerful, but not quite powerful enough to escape. Jupiter sent them flying outward on long, stretched elliptical orbits. These objects didn't stay in the inner solar system, but they couldn't leave it either. They were hurled to enormous distances, hundreds, then thousands of astronomical units, and then the sun's gravity, still barely holding on, pulled them back. Their orbits became enormously elongated. Far out in the distance, galactic forces began to act on them, slowly reshaping those orbits over millions of years. That reshaping is what created the Oort cloud, but we'll get to that in a moment. The point right now is this: Jupiter was the mechanism. Jupiter was the engine that physically moved these objects from the crowded inner solar system to the outer reaches where the Oort cloud could form. Without Jupiter's gravitational influence, there was no force capable of doing this at the scale required. Think about the numbers. The Oort cloud may contain trillions of objects. Those weren't all launched out one at a time over millions of gentle nudges. Jupiter was working constantly across the entire early history of the solar system, scattering material in every direction simultaneously. Some estimates suggest that Jupiter ejected more mass from the solar system than currently exists in any single region except the Sun itself. The sheer scale of what Jupiter did to the early solar system is difficult to overstate. There's something else worth noting here. The specific fates of these objects depended not just on Jupiter's mass, but on its position. Jupiter sits at roughly 5 astronomical units from the Sun, close enough to the inner solar system to intercept material from the rocky planet region, but far enough out to impart the enormous velocity kicks needed to reach the outer solar system. If Jupiter had formed at 3 astronomical units, its gravitational influence would have been named differently. If it had formed at 10 astronomical units, it might not have reached the inner solar system's material effectively enough. The 5 astronomical unit position was essentially ideal for scattering material to the greatest range of destinations. Some of the objects Jupiter scattered didn't go all the way to the Oort cloud. They were sent to intermediate distances and ended up in what we now call the Kuiper belt, the ring of icy bodies beyond Neptune stretching out to roughly 50 astronomical units. These objects received gentler kicks, not enough to send them to the deep outer solar system, but enough to push them past the giant planets. Others received stronger kicks and were launched onto trajectories that took them into the scattered disk, a population of objects with highly inclined and eccentric orbits beyond the Kuiper belt. And then there were those flung to the truly extreme distances, tens of thousands of astronomical units, where galactic tides could begin working on them. Those are the Oort cloud objects. What this means is that Jupiter essentially sorted the early solar system's debris by the strength of its gravitational encounters. A gentle encounter sent something to the Kuiper belt. A stronger encounter sent it to the scattered disk. The most powerful encounters sent material into the deep outer solar system, where the Sun's grip was weak enough for other forces to take hold and circularize those enormous orbits. Jupiter didn't intend this sorting. It was just a consequence of gravity operating across a range of distances and angles. But the result was a structured distribution of material across the entire outer solar system, with the Oort cloud as the outermost product of Jupiter's gravitational work. Here's the thing that makes this genuinely striking. If Jupiter had been even modestly different, say half the mass or twice the mass, or positioned at a significantly different orbital radius, the distribution of scattered material would have been completely altered. A less massive Jupiter might not have kicked objects far enough to reach true Oort cloud distances. A more massive Jupiter might have ejected too much material from the solar system entirely. Very little behind to accumulate in those outer orbits. The Oort cloud's existence, its size, its population, all of it traces back to Jupiter being exactly what it is. The vast frozen shell surrounding our solar system is in large part the legacy of one planet being in exactly the right place, with exactly the right mass at exactly the right moment in the early solar system's history. Getting flung to the outer solar system was only the first half of the journey. Once these objects reached those enormous distances, tens of thousands of astronomical units from the Sun, something else took over. Something most people never think about when they picture the solar system: the Milky Way itself. Here's the thing most people don't realize about gravity at those scales. The Sun is not the only gravitational force that matters out there. At 50,000 astronomical units, the Sun's grip has weakened enormously. And in that weakened state, another force starts to assert itself: the collective gravitational pull of the entire galaxy. hundreds of billions of stars spread across a disk roughly 100,000 light-years wide, all exerting a subtle but cumulative tug on everything in the outer solar system. Astronomers call this the galactic tide, and it works on the Oort cloud the same way the moon's gravity works on Earth's oceans. Think about that for a second. The moon doesn't touch the oceans. It doesn't reach down and pull the water directly. It acts from a distance, creating a gravitational gradient, stronger on the near side of Earth, weaker on the far side. And that difference is enough to raise and lower sea levels by meters, twice a day across the entire planet. The galactic tide does the same thing to orbits. It creates a gradient. It tugs harder on one part of an elongated orbit than another. Over millions and then billions of years, that tugging bends those orbits. It reshapes them. Objects that were launched into extremely elongated elliptical paths gradually have those paths warped by the background gravity of the galaxy. And here's where the numbers get genuinely startling. Up to 90% of all comets that reach the inner solar system may arrive there because of galactic tidal perturbations. Not Jupiter, not a passing star, not some violent collision, just the slow, patient background gravity of the Milky Way, working on these distant frozen objects across timescales that dwarf anything in recorded history. When you watch a bright comet cut across the night sky, leaving a tail of glowing gas millions of kilometers long, there's a good chance the event that sent it inward wasn't anything dramatic. It was the galaxy pulling gently for millions of years until the orbit tipped just enough. That's an extraordinary claim, and it has a very direct consequence for the shape of the Oort cloud. Remember that the Inner Hills cloud is a flattened torus, disc-shaped, roughly aligned with the orbital plane of the planets. The outer cloud is a sphere, a true sphere surrounding the solar system in all directions equally. The reason those two regions have different shapes comes down to which forces have had the most influence on them. The inner cloud is still close enough to the sun and the planets that the plane of the solar system dominates its structure. But the outer cloud has spent billions of years being continuously worked on by the galactic tide, which operates in 3 dimensions. It pulls from above, below, and sideways relative to the solar plane. Over enough time, that 3-dimensional pulling erases the flat structure and produces a sphere. The outer Oort cloud isn't pied like the solar system. It's shaped like the galaxy's influence on the solar system. That's a distinction worth sitting with. But the galactic tide isn't the only external force acting on the cloud. Stellar encounters matter too. The sun is not sitting still in the galaxy. It's orbiting the galactic center, taking roughly 225 million years to complete a single orbit. As it moves, it passes through different regions of the galaxy, through spiral arms, through denser concentrations of stars, through the gravitational neighborhoods of other stellar systems. And every time a star passes close enough to the sun, its gravity reaches into the outer Oort cloud and disturbs things. These encounters don't have to be close by planetary standards to matter. A star passing at 10,000 or even 20,000 astronomical units from the sun, still an enormous distance, can send gravitational ripples through the outermost regions of the cloud. Objects that had settled into stable long-period orbits get nudged. Some get nudged inward. They begin falling toward the sun, arriving in the inner solar system tens of thousands of years later, as long-period comets that no human civilization has ever seen before. These aren't random events. They're predictable in principle, tied to the traffic patterns of the galaxy itself. One star worth mentioning specifically is Gliese 710. It's currently about 62 light-years from the Sun, which is relatively close by stellar standards. Models of its trajectory suggest it's heading our way. In roughly 1.3 million years, it's expected to pass within about 10,000 astronomical units of the Sun, deep enough into the outer Oort cloud's territory to meaningfully perturb objects there. That's not a catastrophe in any immediate sense, but it means a surge of cometary activity in the inner solar system, delayed by tens of thousands of years from the encounter itself. The galaxy sends its signals slowly. Stellar encounters also help explain why the cloud extends so far in every direction. As the solar system has moved through the galaxy over 4.6 billion years, it's experienced thousands of these encounters at varying distances. Each one has stirred the outer cloud differently, nudging objects in different directions, gradually distributing them across the full sphere rather than any particular arc. The cloud's spherical shape isn't just a product of the galactic tide. It's the accumulated result of billions of years of stellar traffic reshaping the population, one gravitational nudge at a time. So when you try to understand what the Oort cloud is, you can't think of it as purely a solar system object. It formed from solar system material, yes. Jupiter threw the pieces outward. But everything that happened after that, the reshaping of orbits, the smoothing of the structure into a sphere, the mechanism that sends comets falling inward, that's the galaxy at work. The solar system formed the cloud's population. The galaxy formed its structure. The Oort cloud is not just a product of our solar system. It's a product of the galaxy we live in. So what's actually out there in all that space? The short answer is trillions of objects. The longer answer is stranger than that and worth sitting with for a moment. Current estimates put the total population of the Oort cloud somewhere around 2 trillion individual bodies. Some models push that number higher, up to 6 trillion. Each one of those objects is less than 100 kilometers across, smaller than a modest moon, frozen solid and drifting in the dark at temperatures approaching absolute zero. Their combined mass is estimated to be somewhere between 10 and 100 times the mass of Earth. That's a significant amount of material. And yet, despite those numbers, if you were somehow transported to a random point inside the Oort cloud, the odds are overwhelming that you would see nothing nearby. Not a rock, not a comet, not a speck of ice. Just empty space in every direction. Here's why that is. The volume of the Oort cloud is almost incomprehensibly large. You have trillions of objects spread across a shell that spans tens of thousands of astronomical units in every direction. The distances between individual bodies on average are enormous, likely measured in astronomical units, not in miles or kilometers. The Oort cloud is dense in the way that a single grain of sand is dense compared to an empty beach the size of a continent. The material is there. It's just that the space between it is so vast that density in any practical sense becomes nearly meaningless. This is not a region you would navigate around objects. It is effectively empty, with the occasional frozen body drifting through the dark at enormous intervals. Now let's talk about what those objects actually are. The composition of Oort cloud bodies is inferred almost entirely from comets, from objects that have fallen inward and been analyzed as they pass through the inner solar system. What astronomers find, again and again, is a mixture of volatile ices. Water ice is the most abundant, but alongside it, methane, ethane, carbon monoxide, hydrogen cyanide, and other frozen compounds. These are not exotic materials. They are the basic chemical ingredients of the early solar system, preserved in exactly the state they were in roughly 4.6 billion years ago. Think about that for a second. These objects have been sitting out there, cold and undisturbed since before the Earth existed. The solar system formed, the planets grew, life appeared, continents drifted, species evolved and went extinct. And out in the Oort cloud, these icy bodies just kept drifting. The temperature out there is somewhere around 4 to 8 degrees above absolute zero. Nothing melts, nothing sublimates, nothing changes. The Oort cloud is a deep freeze on a scale that has no real equivalent. This extraordinary preservation has profound implications for understanding solar system history. The pristine chemical composition of Oort cloud objects serves as a fossil record of sorts, carefully capturing the physical and chemical conditions that existed in the early solar nebula billions of years ago. Each volatile compound, each isotope ratio, each trace element tells a distinct story about planetary formation processes and origins. In this sense, the Oort cloud functions as a vast library of solar system history, with each frozen body representing a volume waiting to be read by scientists. The distribution of objects within the cloud is not uniform. Astronomers believe the Inner Hills cloud holds the majority of the total population. Perhaps 5/6 of all objects reside there in the denser, more compact inner region. The outer spherical shell, despite being vastly larger in volume, contains only about 1/6 of the estimated total. This makes sense given how the cloud formed. Objects flung to the inner Oort cloud stayed more tightly bound to the sun, while those pushed further out got spread across a much larger volume by galactic tides. More volume, lower density, fewer objects per cubic astronomical unit. But here's the thing most people don't realize about everything we just covered. All of it, the population estimates, the mass calculations, the composition data, the distribution between inner and outer regions, all of it is inferred. None of it has been directly confirmed by observation. Not one object has been definitively identified as residing in the Oort cloud. We've never pointed a telescope at a confirmed Oort cloud body and said, "There it is." The distances involved make direct detection essentially impossible with current technology. At 10,000 astronomical units, an object 50 kilometers across would be extraordinarily faint. Even infrared surveys, like the Wide-Field Infrared Survey Explorer, which was specifically capable of detecting cold, dark objects, found nothing. The Oort cloud is too far away, and its objects are too small and too cold and too scattered for us to see them from here. What we have instead are messengers. When a comet falls out of the outer solar system and plunges toward the sun, it carries with it the chemical signature of the place it came from. Its orbit tells us where it originated. Its composition tells us what that region is made of. And from those messengers, arriving one by one over centuries of astronomical observation, scientists have assembled a detailed picture of a population they have never actually seen. It's a remarkable situation. Astronomers are confident enough in the existence of trillions of objects at distances between 2,000 and 100,000 astronomical units to build detailed models of their distribution, composition, and dynamics. That confidence is not guesswork. It is built on orbital mechanics, spectroscopic analysis of comets, and theoretical models of solar system formation that have proven robust across decades of testing. The evidence is strong. The inference is sound. But the objects themselves remain invisible to us. They are out there, drifting in the dark at temperatures barely above absolute zero, carrying frozen water and methane and hydrogen cyanide undisturbed for billions of years. And no human being has ever seen a single one of them directly. Let's talk about what one of these objects actually looks like when it finally makes its way into the inner solar system. We've been discussing trillions of icy bodies sitting in cold storage at the outer edge of the solar system, unseen and undetected. But some of them don't stay out there. Some of them fall inward. And when they do, they become some of the most dramatic things the human eye has ever witnessed in the night sky. The best example we have, the most documented, the most watched, the most recognized comet in human history, is Halley's Comet. Here's where Halley's story begins, and it doesn't begin with Edmund Halley. It begins in the Oort cloud, roughly 4.5 billion years ago. Halley's Comet almost certainly originated as one of those countless icy planetesimals formed in the inner solar system during the early days of planetary formation. Gravitational interactions with the giant planets, primarily Jupiter, kicked it outward into a long elliptical orbit, eventually depositing it in the deep outer solar system. For an enormous stretch of time, it sat out there, frozen, unmoving by any human reckoning, just another anonymous body in a cloud of trillions. Then something changed. A gravitational nudge, possibly from the galactic tide, possibly from a passing star, altered its orbit just enough to send it falling back toward the sun. This is exactly the mechanism we described in earlier sections. The Oort cloud doesn't hold its objects perfectly. It leaks. And Halley's Comet was one of the leaks. As it fell inward, it encountered the giant planets again, and this time, instead of being thrown outward, it was captured. Jupiter's gravity reshaped its orbit from an enormous, sweeping ellipse stretching into the deep outer solar system into something much smaller and much more predictable. The result was a comet now locked into a roughly 75 to 76-year orbit around the Sun, one that carries it from just inside the orbit of Venus out to beyond Neptune and back again. That's still a vast range. But compared to where it came from, it's a tight, controlled loop. Think about that for a second. An object that spent billions of years in the deep freeze, following an orbit so enormous it barely qualifies as a closed path, was gravitationally domesticated. Jupiter tamed it. Now it returns like clockwork. And because it returns on a timescale shorter than a human lifetime, it's the first comet in history that people were able to recognize as the same object seen before. Every other bright comet that appeared in ancient skies was treated as a new event, a one-time phenomenon, a sign, or an omen. Halley's was different. People just didn't know it yet. The historical record of Halley's Comet goes back at least 2,000 years. Chinese astronomers recorded an apparition in 240 BC that matches the calculated orbit. Babylonian records may push it even earlier. Every 75 or 76 years, this object swings through the inner solar system and lights up, developing a coma, a visible atmosphere of gas and dust, and a tail that can stretch for tens of millions of miles. For ancient observers, this was extraordinary. Brilliant, moving, unfamiliar. It generated fear. It generated wonder. Sometimes both at once. The 1066 apparition is the most famous of the pre-modern sightings. It appeared in the sky in the months surrounding the Norman conquest of England, and William the Conqueror's forces took it as a favorable omen. The Bayeux Tapestry, the 230-foot embroidered record of the conquest, depicts the comet directly, with figures below pointing up at it in apparent alarm. That image, stitched into cloth nearly 1,000 years ago, is a record of people watching an Oort cloud object fall through the inner solar system. They had no way of knowing that's what they were looking at. But there it is. It wasn't until the 17th century that the connection was made. Edmund Halley, an English astronomer and a colleague of Isaac Newton, examined historical records of bright comets and applied Newton's newly developed laws of gravity to calculate their orbits. He noticed that comets appearing in 1531, 1607, and 1682 had almost identical orbital characteristics. His conclusion was that these were not three separate comets. They were the same comet returning on a regular schedule. Halley predicted it would return again around 1758. He died in 1742, 16 years before he could see whether he was right. He was right. The comet returned precisely as he calculated, and it was named in his honor. That prediction, made using mathematics, confirmed by observation, was one of the most significant moments in the history of astronomy. It demonstrated that comets were not random visitors. They followed laws. They were predictable. And it opened the door to understanding where they came from. Halley's Comet is classified today as a Halley-type comet, which refers to a broader family of short-period comets with orbital periods between 20 and 200 years. What makes the Halley family unusual is that despite being short-period comets, they're believed to have originated in the Oort cloud rather than the scattered disk. Most short-period comets, the ones with periods under 20 years, are thought to come from the Kuiper belt and the scattered disk, nudged inward by Neptune. Halley-type comets move differently. Their orbits are inclined at steep angles to the orbital plane of the planets, and many travel retrograde, that is, in the opposite direction from the planet's orbits around the Sun. That kind of orbital behavior points to a spherical source. It points to the Oort cloud. The scattered disk doesn't produce retrograde orbits. The Kuiper belt doesn't explain the inclinations. The Oort cloud does. So the Halley family of comets, dozens of objects with similar orbital characteristics, represents a population of one-time Oort cloud residents that were captured by planetary gravity and retained in the inner solar system. Halley's Comet last appeared in 1986 when several spacecraft, including the European Space Agency's Giotto mission, made close approaches and returned the first detailed images of a cometary nucleus. What they found was a dark, irregular object about 15 kilometers long with bright jets of gas and dust erupting from active surface regions. It was ancient material, preserved, almost exactly as it formed 4.5 billion years ago. Every 75 or 76 years, the inner solar system gets a visitor from the deep freeze, and humans have been watching it arrive for more than 2,000 years without knowing until very recently where it was coming from. Halley's Comet is the most famous, but it's far from the most spectacular. In the spring of 1997, something appeared in Earth's night sky that most people alive at the time had never seen before and will never see again. Comet Hale-Bopp reached perihelion in April of that year, and for 18 consecutive months it was visible to the naked eye. Not binoculars, not a telescope, just human eyes, looking up. That had never happened in modern astronomical observation. Comets typically brighten for a few weeks, maybe a couple of months, and then they're gone. Hale-Bopp stayed. It dominated the sky through 2 seasons and burned itself into the memory of an entire generation. Astronomers estimate its orbital period at somewhere around 2,500 years, meaning the next time it swings through the inner solar system, every civilization on Earth today will be a historical footnote. Here's what makes Hale-Bopp so significant beyond the spectacle. It was what astronomers call a dynamically new comet, an object making one of its first passes near the Sun since the formation of the solar system. The volatiles on its surface had never been exposed to significant solar heat. They were pristine, Frozen in place for roughly 4.5 billion years at the outer edge of the solar system, Hale-Bopp came in carrying material that had been sealed in cold storage since before Earth existed. When the sun began heating it, the outgassing was extraordinary. That's why it was so bright. That's why it held together so well and put on such a prolonged display. A comet that's made dozens of previous passes near the sun is depleted. Its most volatile materials are already gone. Hale-Bopp hadn't spent anything yet. Comet Hyakutake appeared just a year earlier in early 1996. It was a different kind of event, faster, more intense, shorter-lived. Hyakutake passed unusually close to Earth, within about 0.1 astronomical units, which is why it appeared so striking despite being a relatively small nucleus. Its tail stretched across a significant portion of the visible sky at its peak. X-ray emissions were detected from it, the first time such emissions had ever been observed from a comet. Like Hale-Bopp, Hyakutake appears to have been a fresh object from the outer solar system, carrying material that had never before been processed by solar radiation. Its orbital period is measured in tens of thousands of years. It came, it blazed, and it's gone for an incomprehensibly long time. These two comets, arriving within a year of each other, gave astronomers a remarkable window into what the early solar system actually looked like. Think about that for a second. The material falling through the inner solar system in 1996 and 1997 had been sitting undisturbed since the planets were still forming. It was a chemical snapshot of conditions from 4.6 billion years ago. Scientists detected water ice, carbon monoxide, methane, dust, complex organic compounds. The ratio of heavy water to ordinary water in Hale-Bopp's coma became one of the key pieces of evidence astronomers use when arguing about how much of Earth's water might have arrived via cometary impact. It wasn't just a light show, it was a laboratory sample from the beginning of time. Virgin comets behave differently from recycled ones. That distinction matters enormously. A comet that's returned to the inner solar system dozens of times has had its outer layers stripped away. What's left is a darker, less active nucleus, coated in processed material. The fresh volatiles are gone. A virgin comet still has those volatiles intact, and when sunlight hits them for the first time, the outgassing is sudden and intense. The comet brightens rapidly. Sometimes it brightens faster than predictions suggest because forecasting the behavior of an object that has never experienced this environment before is genuinely difficult. Astronomers can run the orbital calculations precisely, but the photometric behavior of a fresh comet is harder to pin down. Sometimes that intensity tears them apart. Comet Ison, which made headlines in 2013 as a potential comet of the century, disintegrated as it rounded the sun in November of that year. It likely came from the Oort cloud and was making its first pass near the sun. The heat and tidal forces at perihelion were simply too much for it. This is not unusual. A significant fraction of long-period comets fall apart completely on their first close approach. They've spent billions of years in a frozen, undisturbed state, and the sudden transition to solar proximity is catastrophic. The comet that looks so bright on approach sometimes doesn't survive the encounter at all. What this tells us is that the Oort cloud isn't sending us intact, robust objects. It's sending us fragile, ancient relics. The fact that Hale-Bopp survived its pass and put on an 18-month display was, in some sense, exceptional. Most of what the Oort cloud delivers gets partially or completely destroyed by the experience, and each one that does fall inward gives us a brief, irreplaceable look at chemistry that has been locked away since before any planet existed in a recognizable form. Every comet like Hale-Bopp or Hyakutake carries the same basic story. It formed somewhere in the inner solar system, got thrown outward by gravitational interactions with the giant planets, spent billions of years drifting at the edge of the solar system in temperatures near absolute zero, and then something, a passing star, the galactic tide, a gravitational nudge, sent it falling back inward. In a few months or a few years, it crosses the entire solar system, loses a fraction of itself to the sun's heat, and either loops back outward or never returns. These are objects from the earliest moments of the solar system, preserved near absolute zero for 4.5 billion years, and then suddenly falling through fire. Let's put the Oort cloud scale into the sharpest possible terms, using the only real reference point we have, Voyager 1. Launched in September of 1977, it has been moving away from Earth for nearly 5 decades. Every single day, it covers roughly 1 million miles. That is not a rough approximation. It is the actual sustained velocity of the most distant human-made object ever built. 1 million miles per day. By any standard humans use to measure speed, that is extraordinary. You could circle the Earth 40 times in a single day at that rate, and Voyager 1 has been doing it continuously without stopping since before most people watching this were born. Right now, Voyager 1 sits at approximately 125 astronomical units from the Sun. That means it has traveled about 125 times the distance between Earth and the Sun. Pluto, which we spent most of this discussion establishing as a distant and remote object, orbits at roughly 39 astronomical units on average. Voyager 1 has blown past Pluto's distance more than 3 times over. In 2012, scientists announced that it had crossed the heliopause, the boundary where the solar wind effectively runs out of energy and interstellar space begins. That was a genuine milestone. No human object had ever crossed that threshold before. The heliopause itself represents a profound transition. It marks the point where the sun's magnetic field and solar wind can no longer maintain pressure against the interstellar gas and cosmic radiation that fills space beyond. On one side of that boundary, everything is shaped by our star's presence. On the other side, the sun becomes just one distant light among billions. Voyager 1 had crossed a threshold of genuine cosmic significance, a transition from belonging to our solar neighborhood into truly foreign territory. And yet this crossing, profound as it was, meant almost nothing in terms of the journey ahead. Here's the thing most people don't realize. Crossing the heliopause didn't bring Voyager 1 anywhere near the Oort cloud, not even close. The heliopause sits at around 120 astronomical units. The inner edge of the Oort cloud begins somewhere between 2,000 and 5,000 astronomical units. Voyager 1 has already entered what scientists call interstellar space, and it still has hundreds of years of travel ahead of it before it reaches the beginning of this structure. At its current speed, Voyager 1 will not reach the inner edge of the Oort cloud for approximately 300 years. 300 years. That is not a rounding error. That is not a pessimistic estimate. That is the basic arithmetic of how far the Oort cloud begins and how fast our best spacecraft moves. The American Revolution happened roughly 250 years ago. The invention of the steam engine, the entire Industrial Revolution, the rise of modern medicine, 2 world wars, the space age itself, all of that fits inside a window shorter than what it would take Voyager 1 to reach the beginning of the Oort cloud from where it is right now. And the beginning is not the end. Once Voyager 1 reached that inner edge, assuming the spacecraft were still functional, which it will not be, it would then need to cross through the full depth of the Oort cloud. The outer boundary of the Oort cloud extends somewhere between 50,000 and 100,000 astronomical units from the Sun. Traversing that entire structure from inner edge to outer boundary at Voyager 1's current speed would take approximately 30,000 years. Think about that for a second. 30,000 years. Agriculture was invented roughly 12,000 years ago. The earliest cave paintings in Europe are around 30,000 to 40,000 years old. When humans were making those first marks on stone walls, the light that was just then leaving the sun had not yet reached what we now call the outer Oort cloud. The entire span of recorded human civilization, every empire, every invention, every written word, is compressed into about 5,000 years. Voyager 1 would need 6 of those entire spans, back to back, just to cross the Oort cloud. It is a duration almost unimaginable in human terms, a span of time that dwarfs the entire story of our species as a technological civilization. And this is merely for a spacecraft to traverse a cloud of ice and rock in interstellar space, assuming it somehow retain power and function across 3 centuries of silence and cold. That is a different category of distance than anything we typically discuss when talking about the solar system. Here's where things get even more uncomfortable. Voyager 1 is our fastest long-range spacecraft. It is not slow by any definition humans use for space travel. The Parker Solar Probe, which we've discussed, is faster at its peak, but that peak speed relies on gravity assists near the Sun and cannot be sustained across interstellar distances. In the deep outer solar system, far from any massive body to provide a gravitational assist, Voyager 1's pace is roughly what you'd expect from any craft we've built. There is no fuel depot out there. There is no way to accelerate further. 1,000,000 miles per day is what we have. And that gets Voyager 1 to the Oort cloud in 300 years. Not through it, to it. Let's reframe this one more time, because the numbers alone sometimes don't land the way they should. Voyager 1 was launched in 1977. The scientist who built it, who calculated its trajectory past Jupiter and Saturn and flung it toward interstellar space, many of them are no longer alive. The spacecraft has outlasted careers, institutions, decades of history. It is still out there, still transmitting, still moving. And at this moment, it has not yet reached the postal address of the Oort cloud. It is still in the lobby, so to speak, of the structure we have been describing this entire time. The Oort cloud surrounds everything we have ever sent into space. It surrounds every probe, every telescope, every rocket ever launched. And not a single one of those objects has come close to touching it. The Oort cloud begins where our reach ends, and then extends so far beyond that point that the comparison becomes almost meaningless. There is a version of the solar system that most people carry in their heads, a compact and navigable system where the planets are the main feature and everything else is a footnote. Voyager 1 is the clearest possible argument against that picture. Nearly 50 years of travel, 1,000,000 miles every day, and humanity's greatest explorer is sitting in the driveway. That is the scale we are talking about. One of the genuinely confusing things about the Oort cloud is that it exists in a region where the solar system becomes a surprisingly complicated concept. That sounds like a strange thing to say. The solar system is the solar system. It has a boundary somewhere. But here's the thing. Most people don't realize that boundary is not a single line. It's not a wall. It depends entirely on what you're measuring, and depending on what you measure, you get a very different answer. Start with the heliopause. This is the boundary where the solar wind, the constant stream of charged particles flowing outward from the sun, finally runs out of momentum and becomes negligible against the pressure of interstellar space. Voyager 1 crossed that boundary in 2012 at a distance of roughly 120 astronomical units from the Sun. NASA confirmed that crossing. Scientists declared it the entry into interstellar space, and in one very real sense, that's accurate. Beyond the heliopause, you are outside the bubble of material the Sun pushes outward. The interstellar medium takes over. You are, by that definition, no longer inside the solar system. But here's where things get complicated. The Sun's gravity doesn't stop at 120 astronomical units. It doesn't stop anywhere near 120 astronomical units. Gravity falls off with distance, but it never actually reaches zero. The question becomes where solar gravity becomes too weak to meaningfully hold something in orbit. And that answer is very different from 120 astronomical units. Objects in the outer Oort cloud, sitting at 50,000 or even 100,000 astronomical units from the Sun, are still gravitationally bound. Barely. Their orbits may take tens of millions of years to complete, but they're bound. They will, if left undisturbed, eventually return to the Sun. By the gravitational definition, those objects are still part of our solar system, even though they're sitting nearly a third of the way to the nearest star. This creates a fundamental challenge for how astronomers define and classify these distant objects. An icy body at 50,000 astronomical units from the Sun exists in a region of profound gravitational ambiguity. The solar pull at that distance is so faint that its status feels almost theoretical. Yet, according to orbital mechanics, if such an object were somehow given a nudge inward, the Sun's gravity would eventually recapture it, confirming its membership in our solar system, however tenuous that connection might be. Think about that for a second. Proxima Centauri is about 268,000 astronomical units away. The outer edge of the Oort cloud reaches out toward 100,000 astronomical units. There are objects technically orbiting our Sun that are closer to another star system than they are to the planets. And those objects are still, gravitationally speaking, ours. So which definition do you use? The solar wind boundary at 120 astronomical units, or the gravitational boundary somewhere around 100,000 astronomical units? The answer is genuinely unsettled. Different scientists draw the line differently. The heliopause is clean and measurable. We know Voyager 1 crossed it. We have data. The gravitational boundary is fuzzy by nature. At those extreme distances, the Sun's pull is so weak that the word orbit starts to lose its intuitive meaning. These objects drift. They respond to perturbations from passing stars and from the galactic tide. They're held loosely, the way you might hold something between two fingers with almost no pressure at all. The slightest disturbance can change that. Which brings us to the real ambiguity at the outer edge of the Oort cloud. Beyond some distance, roughly the outermost reaches of the outer Oort cloud, the gravity of other stars begins to compete meaningfully with the Sun's gravity. This isn't a sharp transition, it's gradual. But there is a region where the distinction between gravitationally bound to the Sun and gravitationally influenced by the broader galaxy becomes genuinely unclear. Objects at those distances aren't really orbiting the Sun in any meaningful sense. They're drifting within a gravitational landscape shaped by multiple competing forces. The Sun is still the dominant influence, but barely. And sometimes, that balance gets disrupted entirely. When a star passes close enough to the outer Oort cloud, and over the solar system's 4.6 billion year history, many stars have passed at various distances, its gravity can exceed the Sun's hold on an individual object. When that happens, the object gets stripped. It no longer belongs to our solar system. It gets liberated into true interstellar space, becoming a rogue body drifting between the stars. no longer bound to any star, just traveling through the galaxy. This is not theoretical in the distant sense. It has certainly happened. Over billions of years, the Oort cloud has almost certainly lost material to close stellar encounters. Objects that were once gravitationally ours have been pulled away and are now traveling somewhere between the stars, detached from any parent system. And conversely, interstellar objects can fall inward and get captured. Oumuamua and Comet Borisov were detected in recent years as interstellar visitors, objects from other star systems that briefly passed through our solar system. The boundary between solar and interstellar is not just ambiguous in concept, objects actually cross it. What this means is that the edge of the solar system is less like a border and more like a contested frontier. The inner planets exist in a region where the sun's dominance is total and undisputed. The outer Oort cloud exists in a region where the sun maintains a claim, but that claim is increasingly fragile the farther out you go. At some distance, that claim dissolves. The transition from solar system to interstellar space isn't a line on a map. It's a gradient, a slow loosening of gravitational grip, influenced by the galaxy, by passing stars, by forces operating on timescales we can barely conceive. The Oort cloud straddles that frontier, which makes it one of the most unusual structures in all of astronomy. The Oort cloud is not a static structure. That's one of the things that makes it genuinely unsettling. Everything we've talked about so far, the scale, the structure, the trillions of icy bodies sitting in cold storage at the edge of the solar system, might suggest something fixed, frozen, permanent. But the outer Oort cloud exists at distances where the sun's gravitational grip is barely holding on. That means other forces can reach in and disturb it. Those forces have been doing exactly that for 4.6 billion years, and they're doing it right now. Here's the mechanism. As the sun orbits the center of the Milky Way, it moves through a stellar neighborhood that is constantly slowly shifting. Other stars drift past at various distances over millions of years. Most of these encounters happen at enormous distances, thousands of astronomical units, sometimes tens of thousands. At those ranges, you might expect nothing significant to happen, but the outer Oort cloud is sitting at those exact distances. A star passing at 10,000 astronomical units isn't passing through empty space. It's passing through the outer Oort cloud itself, or close enough that its gravity sends ripples through that region. Objects that were sitting in stable, long-period orbits get nudged. Some of those nudges are small. Others are enough to send an icy body falling inward toward the sun, beginning a journey that will take hundreds of thousands of years before it ever approaches the inner solar system. This is not a rare event in astronomical timescales. It's essentially continuous. Stellar encounters capable of meaningfully perturbing the outer Oort cloud occur roughly every few million years. Over the full age of the solar system, that adds up to thousands of individual encounters, each one sending a new wave of objects inward. The comet showers these encounters trigger don't arrive all at once. They spread out over millions of years. But the underlying driver is the same. A star passed too close. Gravity did its work. Objects that had been frozen in place for billions of years began falling. One specific case is worth paying close attention to. The star Gliese 710 is currently approaching our solar system, based on precise measurements from the Gaia Space Observatory. Astronomers have calculated that Gliese 710 will pass within roughly 10,000 astronomical units of the Sun in approximately 1.3 million years. Think about what that means. That's not a near miss in stellar terms. That's a direct passage through the outer Oort cloud. A star moving through that region will gravitationally disturb a massive volume of the cloud. The resulting comet shower could persist for millions of years afterward, steadily delivering dislodged objects into the inner solar system. We know this is coming. We just can't know exactly what it will look like when it arrives. And then there's a more extreme version of this idea. In the 1980s, astronomers noticed something curious about the timing of mass extinction events in Earth's fossil record. Several researchers, including physicists Richard Muller and Mark Davis, proposed that the apparent periodicity of these extinctions, roughly every 26 to 30 million years, could be explained by a companion star to the Sun. They called it Nemesis. The hypothesis was straightforward. If the Sun had an undetected dwarf star companion orbiting at a very large distance, that companion would periodically swing close enough to send a comet shower raining into the inner solar system, triggering impacts, triggering extinctions. Nemesis has never been found. Extensive infrared sky surveys have searched for any object that could be an undetected companion star. Nothing has turned up. The extinction periodicity itself has also been questioned. More recent analyses of the fossil record suggest the timing may not be as regular as it initially appeared. The Nemesis hypothesis for now has fallen largely out of favor. But here's the thing. The fact that serious astronomers proposed it at all, that it was considered a legitimate scientific hypothesis for decades, tells you something important about how the field thinks about stellar perturbations. The idea that a comet shower could cause a mass extinction on Earth wasn't the speculative part. That part was accepted. What was debated was only the trigger, whether it was a companion star or simply the random encounters with passing stars that happen anyway. The disruption mechanism itself was never really in doubt. The galactic tide compounds all of this. The Milky Way's gravitational field tugs on Oort cloud objects continuously, bending orbits gradually over millions of years. Stellar encounters provide sudden, sharp perturbations. The galactic tide provides a slow, constant background reshaping. Together, these two forces are responsible for the vast majority of long-period comets that enter the inner solar system. The Oort cloud responds to both on timescales so long that from any human vantage point it appears completely still. But it is not still. It is being worked on continuously by forces operating at galactic scales. What this means is that the Oort cloud is not just a fossil record of the solar system's formation. It's a living system in the sense that it's constantly being perturbed, reshaped, and depleted. Objects are always falling inward. Stellar encounters are always nudging new populations of bodies onto new trajectories. The cloud we have today is not identical to the cloud that existed a billion years ago. Stars that passed through it long before humans existed left gravitational fingerprints on the orbits of objects still falling toward us today. Every comet that has ever lit up Earth's night sky was likely set in motion by an event that happened long before any human was alive to see it. There's a dimension to the Oort cloud that most people never consider, which is what it means for life on Earth. Not just in the abstract sense of space being dangerous, in a direct, specific, and genuinely strange sense, the Oort cloud has a relationship with life on this planet that cuts both ways. It may have helped create the conditions for life. It has also, on multiple occasions, done its best to destroy it. Let's start with the constructive side of that equation. When Earth formed roughly 4.6 billion years ago, it was a hot, violent, largely dry world. The processes that build rocky planets don't deliver much water. The temperatures close to the sun during planetary formation are too high for water ice to condense into the material that becomes terrestrial planets. So where did Earth's oceans come from? This is a question astronomers have been wrestling with for decades. One of the leading answers involves comets. During a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago, the inner solar system was pelted with an enormous volume of material from the outer solar system. Gravitational instabilities among the giant planets sent waves of debris inward. Some of that debris came from the same population of icy objects that eventually settled into what we now call the Oort cloud. Comets, water-rich, volatile-laden bodies, slammed into the early Earth in enormous numbers. Each impact delivered water. Over hundreds of millions of years, those impacts may have contributed meaningfully to the oceans that now cover roughly 71% of this planet's surface. Here's where things get more interesting. Water wasn't the only thing those comets were carrying. Comets are not just balls of ice, they are chemical libraries. When astronomers study comets passing through the inner solar system, they find amino acid precursors, complex organic molecules, the kinds of compounds that serve as the building blocks of biological chemistry. Comet Hale-Bopp, which passed through in 1997, carried glycine, the simplest amino acid. Other comets have yielded compounds like formaldehyde and hydrogen cyanide, which under the right conditions can combine to form more complex organic structures. Think about what that means for a moment. The same frozen debris that was scattered to the outer solar system by Jupiter's gravity 4.6 billion years ago, sitting in cold storage in the Oort cloud for billions of years, may have eventually found its way back inward and delivered some of the raw chemistry that made life possible on this planet. The Oort cloud is not just a reservoir of ice. It may be, in part, a reservoir of the ingredients for biology. But here's the other side of it. Comet impacts are not gentle events. An object even a kilometer across, hitting the Earth at tens of kilometers per second, releases energy that dwarfs the most powerful nuclear weapons ever built. A 10-kilometer impactor produces a global catastrophe. The atmosphere ignites. Debris fills the sky. Sunlight is blocked for months or years. Ecosystems collapse. Most species don't survive. The KPG extinction event, the one that ended the reign of non-avian dinosaurs roughly 66 million years ago, is attributed to an impactor, most likely an asteroid, but the broader class of large impactor events includes comets. The Chicxulub crater in Mexico, roughly 180 kilometers across, is the scar that event left behind. In the space of a few 100,000 years following that impact, approximately 75% of all species on Earth went extinct. That's what the Oort cloud is capable of sending our way. Some researchers have gone further. They've looked at the geological record, the pattern of mass extinctions over the past several 100 million years, and argued that there's a rough periodicity to these events. Something like a cycle repeating every 26 to 30 million years. The explanation that's been proposed for this pattern is stellar perturbation of the Oort cloud. As the Sun orbits the galaxy, it periodically passes through denser regions of the galactic plane or gets close enough to molecular clouds and passing stars to disturb the outer Oort cloud. That disturbance sends a wave of comets inward. Comet flux in the inner solar system spikes, impact rates go up, and on Earth, extinction rates climb with them. This is speculative. The data is noisy, and the periodicity isn't universally accepted. But the mechanism is real. Stellar encounters do perturb the Oort cloud, and elevated comet activity in the inner solar system would have consequences. The idea that the history of life on Earth has been periodically shaped by the gravitational state of a cloud of frozen objects trillions of miles away is not a fringe claim. It's a serious scientific hypothesis, and it reframes the Oort cloud completely. This isn't just an astronomical curiosity at the edge of the solar system. It's a structure with a direct line of influence to the history of every species that has ever existed on this planet. The water in your body may have arrived here via comets from the outer solar system. The organic compounds that kicked off early chemistry on Earth may have the same origin. And the mass extinctions that reset the evolutionary clock, the ones that shaped which lineages survived to eventually produce us, may owe something to the dynamics of a cloud we've never directly observed. The same cloud of ice and rock that may have helped start life here has also, on multiple occasions, come very close to ending it. Let's be honest about something. The Oort cloud is, for all practical purposes, unreachable. Not difficult to reach, not a challenge for future engineers. Unreachable, at least on any timescale that a human civilization can meaningfully plan around. Désolé. Here's where things get uncomfortable. Voyager 1, which we've already discussed, has been traveling for nearly 50 years. It's moving at roughly 1 million miles per day, and it won't reach the inner edge of the Oort cloud for approximately 300 years. That's our fastest long-range spacecraft. 300 years just to touch the beginning of it. So let's say we wanted to actually send a dedicated probe to the Oort cloud, something designed to study its objects up close. What would that require? Even if you could build a spacecraft 10 times faster than Voyager 1, you're still looking at 30 years just to reach the inner edge. To get deep into the cloud, to the region between 20,000 and 50,000 astronomical units where the bulk of the long-period comets originate, you'd need a spacecraft that could somehow travel for centuries while still functioning, still transmitting, still doing science. Damwati, think about the engineering problem that creates. The most durable spacecraft ever built are measured in decades. Voyager 1 is a remarkable exception, still operational after 47 years, but it was never designed to maintain its systems for 300 years. Electronics degrade, power sources deplete. Radioisotope thermoelectric generators, the kind that power deep space probes, have operational lifetimes of perhaps a few decades before their output drops too low to be useful. A mission to the inner Oort cloud isn't an engineering stretch. It's an entirely different category of problem. You'd need power systems, computing systems, and communication hardware that can survive for centuries in deep space. Nothing close to that has ever been built. And then there's the communication problem. At 2,000 astronomical units, a radio signal traveling at the speed of light takes roughly 11.5 days to reach Earth. At 50,000 astronomical units, that same signal takes nearly 290 days each way. You'd send a command to adjust the spacecraft's instruments and wait almost 2 years for a confirmation that the command was received. Any real-time control is completely impossible. The spacecraft would need to operate autonomously, making its own decisions, running its own science, for years between each communication window. That's an artificial intelligence and software reliability challenge that doesn't currently exist in any space agency's toolkit. So direct exploration is for now off the table. That leaves indirect detection. And here, the results are equally sobering. The Wide Field Infrared Survey Explorer, known as WISE, conducted one of the most comprehensive sky surveys ever attempted. It scanned the entire sky in infrared, specifically the kind of wavelengths that icy cold objects tend to emit. Oort cloud bodies should, in principle, be detectable this way. They're cold, but they're not completely dark. WISE found no confirmed Oort cloud objects, not one. The reason is simple once you work through the numbers. An object 50 kilometers across, sitting at 50,000 astronomical units from the Sun, reflects almost no sunlight and emits almost no heat. It is, for all observational purposes, invisible. Even our best infrared telescopes aren't sensitive enough to pick them out from the background noise of the universe. There's one technique that might eventually work: stellar occultations. The idea is this: when an Oort cloud body passes directly between Earth and a distant star, it briefly blocks the star's light. The dimming lasts only fractions of a second, but it's detectable in principle. The challenge is that you'd need to monitor millions of stars simultaneously, continuously, with extremely high time resolution to have any meaningful chance of catching one of these events. The statistical probability of any given star being occulted by any given Oort cloud object at any given moment is incredibly small. You'd need enormous survey campaigns running for years. Some research groups have attempted this, and there are a handful of candidate detections, but nothing confirmed as a genuine Oort cloud object. The technique remains promising in theory, but unproven in practice. What would an actual mission to the Oort cloud look like if you genuinely tried to design one? Engineers and theorists have sketched out concepts. A nuclear-powered spacecraft, possibly using a nuclear-electric propulsion system, could potentially reach velocities of 20 astronomical units per year or more. At that speed, the inner edge of the Oort cloud is roughly a century away. You'd launch the mission today, design everything to function until the mid-22nd century. Choose a target object that you can't actually confirm exists yet, and aim for a region of space defined primarily by the orbital behavior of comets rather than direct observation. Even in the most optimistic scenarios, a mission like this is a multi-generational commitment. You launch it, and your grandchildren's grandchildren receive the first data from the destination. The strange reality is this: we know more about galaxies billions of light years away than we know about a structure within our own solar system. We can image the jets of distant quasars. We can map the cosmic microwave background radiation from the early universe. We can detect gravitational waves from merging black holes a billion light years away. And yet the Oort cloud, which sits within the gravitational territory of our own star, remains essentially invisible to us. Everything we know about it is inferred. The trillions of objects believed to reside there have never been directly confirmed. The Inner Hills cloud, where the majority of the population is thought to concentrate, has never been imaged. The outer spherical shell, extending nearly a third of the way to Alpha Centauri, exists. TS in our models and in our mathematics, but not yet in our observational data. That's an extraordinary situation. The most remote part of our home solar system is more mysterious than objects that took the universe billions of years and the light from dead stars just to reach us. The Oort cloud may be the one part of our solar system we will never truly explore, not in any time frame that means anything on human scales. So step back and take all of this in. Everything we've covered: the Inner Hills cloud beginning at 2,000 astronomical units, the outer spherical shell stretching to 100,000 astronomical units, the trillions of icy bodies shaped by galactic tides, the comets falling inward over millions of years, all of it points to a single conclusion. The solar system is not what most people think it is. We grew up with a picture of 8 planets, maybe a belt of asteroids, maybe Pluto hanging out at the edge. That picture is a cartoon. The actual solar system extends almost a third of the way to the nearest star. It is a gravitational empire of staggering proportions, and nearly all of it is the Oort cloud. Here's the thing that is genuinely hard to sit with. Every spacecraft we have ever launched, the Voyagers, the New Horizons probe, the Parker Solar Probe, every single one of them is still, by any meaningful measure, in our immediate cosmic backyard. Voyager 1 has been flying for nearly 50 years. It hasn't reached the beginning of the Oort cloud yet. The planets, all 8 of them, exist within a region that represents less than 1% of the full radial extent of our solar system. We live in a tiny warm pocket close to the sun. Surrounding that pocket in every direction is this enormous frozen shell that we have never visited, never photographed directly, never will in any time frame that matters to a human being. Think about what that means. When astronomers say our solar system, they mean a structure that reaches 100,000 astronomical units in every direction. A sphere, not a disk, not a flat ring, a sphere surrounding us completely, filled with trillions of preserved objects from the earliest moments of solar system formation. Some of those objects are older than Earth. Some of them carry the organic compounds that may have helped start life here. And they have been sitting out there, in the cold, in the dark, for 4.5 billion years, waiting for something to nudge them inward. That nudge could come from the galaxy itself, the galactic tide, the slow gravitational pull of the Milky Way, reaches all the way out to those objects and tugs on their orbits. A nearby star passes at some distance, sends a ripple through the outer cloud. A trillion-year-old block of ice begins its long fall toward the sun. That fall takes tens of thousands of years. And eventually, if we happen to be watching at the right moment in history, we look up and see a bright streak in the night sky, and we call it a comet. That comet came from the Oort cloud. It came from a region so far out that it borders on interstellar space, a region shaped by forces operating on galactic scales, a region that most people have never heard of and that no spacecraft has ever reached. And it is technically part of our solar system. If you found this kind of exploration as striking as we have, spend a moment giving this video a thumbs up and subscribing. It helps more curious minds find their way to content like this. It means we can keep going deeper. The full picture of our place in the cosmos shifts when you account for the Oort cloud. We are not inhabitants of a modest system of 8 planets orbiting a medium-sized star. We are inhabitants of an enormous gravitational territory stretching a light year in every direction. A territory shaped by billions of years of planetary violence, galactic forces, and stellar encounters. The planets we know, the ones with names, the ones in the textbooks, they're the center of something far larger than any diagram has ever shown. And that structure, that vast frozen shell surrounding everything we have ever known, is being reshaped right now. The galaxy is pulling on it. Stars are slowly drifting past at distances that will, in millions of years, send new ripples through the cloud. New comets will begin their long fall inward. Some of them will reach the inner solar system long after any civilization we could recognize has come and gone. When you next gaze upward at the stars above, you're not looking at the edge of anything. You're standing inside a structure so vast it almost reaches the stars. The stars themselves are just the beginning.